Hello, everyone. I'm Tejumade Afonja.
Hi, everyone. I'm SautiDB-Naija.
We are presenting to you our paper titled Learning Nigerian Accent Embeddings from Speech, a preliminary result based on SautiDB-Naija Corpus. The performance of voice-controlled systems is usually affected by the accented speech of the speaker. But this is not the motivation of our project. In our project, we are interested in techniques that can facilitate the translation of one accent into another. The reason for this interest lies in our hypothesis formulated from our collective experience that the speaker's accent plays an important role in the listener's understanding. To test this hypothesis, we conducted a 6-month survey that brought in over 374 responses from more than 38 countries, including 26 African countries. The results of our survey provide further evidence to support our hypothesis. Previous studies have shown the capability of neural networks for accent translation. Such models require data on different accents from which speaker-independent accent embeddings can be learned and applied. As a result of this, our study proposes a dataset for learning different Nigerian accents. SautiDB-Naija is an accented speech corpus of non-native English speech, which contains 919 speech recordings from an assemblage of different L1 speakers, namely Yoruba, Igbo, Edo, Efik Ibibio, and Igala. In addition to this, we also present preliminary results that is based on our first attempt at using our data to learn accent embeddings. So we created a standard benchmark dataset, which we can use to learn accents. Our dataset collection effort is still ongoing, and you can contribute to it using the link provided. Now we discuss our modeling approach.
To quantify the accent information access in our proposed dataset corpus, we have set up a modeling task to learn speaker-independent embeddings, accent embeddings in this case. Specifically, these accent embeddings should be similar in case of different speakers who speak with similar accent. And for this modeling task, we have designed a very simple architecture, which is an encoder classifier architecture. The encoder comprises a feature extractor and a gated recurrent unit recurrent neural network on top of each other. Specifically, the feature extractor takes in raw audio and produces a feature representation, which is fed to the gated recurrent unit, or GRU for short. The output of the GRU is the accent embedding, and this embedding is then passed into the classifier head, a single linear classifier, which outputs the accent probability or the accent class probability for each accent class considered. For the case of our own experiment, we tried 2 different feature extractor types in our encoder, and they are specifically MEL spectrogram and WAV2VAC. MEL spectrogram is simply a frequency domain representation of time series speech signal. And since it's an handcrafted representation, it requires no parameter training, and which means that there is no parameter overhead in the training procedure. WAV2VAC, which is the second representation, which we experimented with, is a self-supervised pre-trained model that encodes general information of audio in 2 dimensions and has been trained with a contrastive loss. However, it comes with some compute overhead since it adds some parameters to the training procedure. Our experiments are set up in this way. First, we compare Bell spectrogram and WAV2VEC encoders feature extractors and train those models. Then the best model which has been obtained in this comparison is then improved using batch normalization to the output of the feature extractor. We then compare these 2 trained models to a base model, which is simply a pre-trained WAV2VEC and a randomly initialized GRU and linear classifier. The point of this base model is to prove that our model actually goes from not knowing any information about accent into learning accent information and being able to classify speech dataset into accent classes. Our results are shown in this table, and as can be seen, going from our base model to our best model, we more than doubled the accuracy and the F1 score of our models. Also, going further, now taking a look at the 2-dimensional projection of these embeddings using the principal component analysis, specifically the first 2 principal components, we can see in the plots shown in this current slide, a 2-dimensional projection of these embeddings in our test dataset. And specifically, we see that there are clusters which have been formed for the 3 different accents considered. In the upper left corner of the plot, we find the Yoruba accent. And below the Yoruba accent, just in the lower left, we can find the Edo accent. Also, the interesting part of what can be seen here is that the Yoruba and the Edo accent also share cultural history, which means that they are related. And as can be seen in our embedded space, they also are much closer to themselves than the 3rd accent considered here, which is the Igbo accent, which is on the right. This information shown proves that there is indeed some fidelity in the accent information provided in our corpus and shows the potential of this dataset for applications that vary from accent translation and to other kinds of voice-enabled AI modeling. Now we go to the conclusion.
So in conclusion, we have presented SautiDB-Naija, an English database of non-native Nigerian accents to support accent conversion or translation task. Our results and experiment are pointed towards possible future use case of SautiDB-Naija. And for our future work, we will focus on significantly expanding and diversifying our corpus while also commencing research in other L2 conversion tasks. Our project would not be the same without a team of 11 people who are scattered across 4 different continents. Thank you. If you have any question, kindly reach out to us at research@aisaturdaylagos.com.